Hello everybody, welcome back to Calculus 1 online at FCC with Professor Lachman. In this lecture we will discuss L'Hopital rule, which is a very useful method for computing limits using derivatives. Now that we have learned all the main rules of differentiation and also discussed several application problems of derivatives, we can revisit the idea of limits. So this is something that we have talked about early in the semester, and now we can apply a new method to computing limits, and that is L'Hopital rule. So L'Hopital rule is applicable whenever we have the following two forms, 0 over 0 or infinity over infinity, and we're going to refer to those as indeterminate forms. Now, there are other cases that we will consider in today's lecture. However, these two are the most important ones. Now, we briefly talk about 0 over 0 early in the semester, and at the time we didn't know how to compute derivatives, so we had to use different tricks such as multiplication by a conjugate and factoring. So now we're going to revisit some of those problems and apply a different method. So let's take a look at the formal statement of L'Hopital rule, the case 0 over 0. This says the following. Suppose f and g are differentiable functions over an open interval containing point A, except possibly at A. That is, our functions f and g don't necessarily have to be differentiable at A. Then, if the individual limits as x approaches A of the functions f and g are 0, that is, we have 0 over 0 form, then what we can do to compute this limit is take the derivative of f, take the derivative of g, and then take a look at that limit instead. Okay, so notice what we have here. We do not do the quotient rule, but rather we just take the derivative separately and evaluate this new limit. Very similarly, we're going to apply the same trick whenever we have infinity over infinity case, okay? And notice that we can have positive or negative infinity. The sign doesn't matter. That is, if you plug in a for x in f and g, you're going to get the following form, infinity over infinity. And if that is the case, all we need to do is take the derivative of f and then the derivative of g, okay? Take that ratio and then find the limit as x approaches a. All right, and all of that will make a lot more sense once we actually take a look at the examples. Now let's take a look at the first set of problems where we need to compute limits of the form 0 over 0. You will notice that I wrote out all solutions by hand, and this is to give you an idea of what is expected from your solutions. So let's take a look at the first problem. We have the following limit as x goes to 0 of the expression square root of 1 plus x minus square root of 1 minus x. That's in the numerator, and then we have x in the denominator. So let's see the solution. First step is to evaluate this expression at x is equal to 0, and I'm doing it over here. And notice we get 0 over 0, which is one of the two forms where the L'Hopital rule is applicable. So now that I've established that the rule is applicable, we're going to take the derivative of the top and derivative of the bottom. The derivative of x is 1, so that's easy. And then the derivative of the numerator is 1/2 times 1 plus x raised to the negative 1/2 plus 1/2 times 1 minus x raised to the negative 1/2. And now that we have learned all the rules and mastered them, I'm going to let you check your work and make sure that you get this result. So the limit as x goes to 0 of this expression right here, I'm going to rewrite it as 1 over 2 root 1 plus x plus 1 over 2 root 1 minus x is no longer of the form 0 over 0. When we plug in x is equal to 0, we just get a number, and that is 1. Okay, so that's the limit. And of course, we can check our result by using a graphing calculator or Desmos. So this is me checking my answer. And notice as we get closer to 0 from either side, what happens to the function? The function value is 1. All right, so we have our confirmation that the limit is indeed 1. Okay, let's take a look at the next example. Example 2. We have the limit as x goes to 0 of the following expression, e to the x minus 1. That's in the numerator, and then x squared is in the denominator. Same idea. The first step is to plug in x is equal to 0 and confirm that we're working with one of the two forms. It is 0 over 0 in this case, so that means we can apply L'Hopital rule. I'm computing the derivatives. Okay, so e to the x minus 1, that's the derivative of the numerator, and then 2x, that's the derivative of the denominator. We plug in x is equal to 0, and we get 0 over 0 again. So here's our first example where we apply this rule multiple times, and you can apply it as many times as needed. As long as you get that form 0 over 0, you're good to go, and you can apply it multiple times. All right, so now the derivative on the top is e to the x. The derivative on the bottom is 2. And once we evaluate this at x is equal to 0, we just get a number. So 1/2 is our answer for this limit. Once again, let's go ahead and check it with the graph. As we approach 0 from either side, either left or right, the function is going to 1/2. Okay, so that is your second example of a limit where we have 0 over 0. And notice that while the first problem we could solve by multiplying by a conjugate, the second problem we don't really have a method because factoring here wouldn't work. We don't really have the right expression to apply multiplication by a conjugate. So L'Hopital rule here is the way to go. All right, let's take a look at the third example. We have limit as x goes to 0 of the expression sine of 4x over 3x. Let's review the solution. First step is the same. We're going to plug in 0 for x. We get our form 0 over 0, which means we can apply this rule. Okay, I'm computing the derivative on top and the bottom. So the derivative on top is 4 cosine of 4x. The derivative in the denominator is 3. Okay, and now we evaluate this expression at 0. We get 4 cosine of 0 over 3. Cosine of 0 is 1. So the final answer is 4 over 3. And last step is to check with the graph. Okay, so here is a partial graph of this function sine of 4x over 3x. We're only interested in the behavior of this function around 0. And notice as we approach 0 from either side, the function is approaching 4/3. Okay, so this is your first set of problems where the limits are of the form 0 over 0. Notice the expression can be all sorts of functions. We have exponentials, we have radicals, we have trig functions. So there's just not one type of functions that we can have. Okay, as long as you have 0 over 0, you can apply this rule. And here I'm also checking my result with the graph. Okay, so here and here, these are the visual confirmations that my limit was computed correctly. That is not something you will need to do on your homework, but I think it's very important to see that graphical connection, and if you're working on a quiz or if you have the time to check it on the homework, I strongly recommend doing it. Now let's take a look at the second set of problems, and here we will be working with the second indeterminate form, infinity over infinity. So here is our first problem. We would like to compute the limit as x goes to infinity of the rational function 4x cubed minus 6x squared plus 1 over 2x cubed minus 10x plus 3. Let's take a look at the solution. So if I plug in infinity, and I use that in quotation marks, that is if I plug in a really big number for x in both top and bottom, I get infinity over infinity. Okay, and that means we are able to apply L'Hopital rule. So we compute the derivative on top and the bottom. The derivative on top is 12x squared minus 12x. The derivative on the bottom is 6x squared minus 10. And once again, we get the same form as before, infinity over infinity. So we can apply L'Hopital rule the second time. So once we compute the derivatives of these functions right here, we get 24x minus 12 over 12x. That is still infinity over infinity. Think about plugging in a really large number for x. All right, so that means we can apply L'Hopital rule again. So here we apply 3 times, and here we just get 24 over 12, which is equal to 2. Now this result shouldn't be very surprising because this is one of the problems that we could have solved without using the rule. And why is that? This is one of the examples that we discussed early in the semester where we have a rational function with polynomials of the same degree on top and the bottom. So all we have to do is take the ratio of their leading coefficients and we get 2, which is the same outcome. All right, and we can also check it with the graph. So here's the graph of this function. Notice what happens at infinity. As x goes to infinity, this branch approaches 2. So this horizontal line is y is equal to 2. Okay, so that's your visual confirmation that our limit was computed correctly. Okay, let's take a look at the second problem. Okay, we have limit as x goes to infinity of the following expression. Natural log of 9x over 5x. All right, so what is the solution to this problem? Again, if we plug in a really large number for x, we know that natural log function looks something like this. So this is going to go to infinity. And 5x, that's a straight line. That's through the origin with a slope of 5. So that also goes to infinity. Okay, so we get the case of infinity over infinity, which means we can apply the L'Hopital rule. So we take the derivative on top, divide by the derivative on the bottom. Okay, so that will be 1 over 9x, and by chain rule, times 9. Okay, and the derivative on the bottom is just 5. So we need to compute the limit as x goes to infinity of the expression 1 over 5x, and that is clearly 0. Okay, so this result shouldn't be very surprising either. Why is that? Well, if you just take a look at the way the two functions behave, 5x and natural log of 9x, 5x grows much faster than natural log of 9x. Okay, you can see it by just looking at this very non-precise graph, right? So 5x grows to infinity very quickly, while natural log of 9x doesn't do that. Okay, it is still going to infinity. So in a way, the denominator is dominating in this case. So it makes sense that the ratio is going to 0. And we can also check by looking at the graph of the function natural log of 9x over 5x. Okay, notice what happens as x goes to infinity. We have this asymptotic behavior. The branch of the function, it's also approaching the x-axis. Okay, so you can confirm your result with the visual representation. All right, so the limit here is 0. Okay, one more example to consider of the form infinity over infinity. So here's our third problem. Limit as x goes to infinity of the following expression: e to the power 3x over 3e to the power 3x plus 5. All right, so let's see what we get here. Again, if we plug in a really large number for x, we're going to get infinity over infinity, because e to the 3x, that's an increasing function, exponential growth here. So we get infinity on top and infinity on the bottom. So we can apply L'Hopital rule. I'm going to take the derivative. So on top we get 3e to the power 3x. On the bottom we get 9 e to the power 3x, and these expressions cancel out. Okay, so we just get a constant term, 3 over 9 or 1 over 3. All right, and we can confirm by sketching our function. So I'm sketching this function right here. Notice what happens as x goes to infinity, the branch is approaching 1 over 3. Okay, you can always check this by graphing the limit. Okay, so in this case, what you would plug in is y is equal to this expression right here, and that's going to be the black curve, and then y is equal to the constant term, that's the dashed line right here, and you can see, yes, we have this behavior where the branch is slowly approaching the horizontal line. Y is equal to 1 over 3. Okay, so once again, notice what type of functions we have here. We have polynomial functions, logarithmic, and exponential. So all sorts of examples are possible. So what we need to do for this case right here is check that we get infinity over infinity. And you might have to apply the rule several times. That's okay. And eventually, for the problems that are selected in our course, you will get a number. And of course, graphing. Okay, always check your work by sketching your functions, either using Desmos or a graphing calculator. Now let's take a look at some examples where we do not get one of the two standard forms. That is, we don't get 0 over 0 or infinity over infinity, but rather we get something like this. We get 0 times infinity or infinity times 0. Let's take a look at the first problem. This one says we have a limit as x goes to infinity of the expression x squared times sine of 1 over 4x squared. So if we plug in a really large number for x, what do we get? We get infinity over here times what? Well, 1 over 4x squared, that goes to 0 for really large value of x, and sine of 0 is 0, so we get infinity times 0. So how do we approach this type of problem? Whenever this is one of the forms, we cannot apply L'Hopital rule directly, but the first step is to convert our expression into one of the two forms, either 0 over 0 or infinity over infinity. And by converting, I mean rewriting, just using some algebraic tricks, not really changing the expression, but rewriting it so that we have one of these two forms. So what is the trick here? What we're going to do, we're going to take x squared and you can write it as 1 over x squared. Okay, that is exactly the same expression. Okay, so now our new representation is this: sine of 1 over 4x squared over 1 over x squared. And that is very useful because now I have 0 over 0. Okay, why is that? Because as x gets really, really big, 1 over x squared, that goes to 0. And now I can apply the rule. All right, so now we compute the derivative on top and the bottom. On the top, we get cosine of 1 over 4x squared times negative 1 over 2x cubed. So this is chain rule. I'm going to let you confirm that result. And then on the bottom, the derivative of 1 over x squared is negative 2 over x cubed. Okay, and we can clean this up and cancel out 1 over x cubed. So the answer here is 1/4 times cosine of 1 over 4x squared. Now, as we take the limit of this expression, what happens here? 1 over 4x squared, this expression goes to 0 as x gets really, really big. Cosine of 0 is 1, so we just get 1/4 times 1, and that is where 1/4 comes from. Okay, so carefully go through all of the steps of this solution and make sure that everything is clear. And of course, we can check this with a graph. So here is my graph of this function, x squared times sine of 1 over 4x squared. Okay, we're interested in the behavior of this function as x goes to infinity. And here is my y equals to 1/4. That's the horizontal line, and notice that my graph is approaching that line. Okay, so you can always check with the graph and make sure that your limit is computed correctly. Okay, let's take a look at the second example. So second example is limit as x goes to infinity of the expression x times e to the power negative 4x. All right, similar idea here. We get infinity for the first term, and then e to the negative 4x. As x goes to infinity, this expression vanishes, right? It goes to 0. So we have infinity times 0, and that means we need to convert it to one of the two main forms, right? 0 over 0 or infinity over infinity. So this one is fairly straightforward. Okay, we just rewrite e to the power negative 4x as 1 over e to the power of 4x, right? So this one is kind of obvious what to do here. And what happens now? Now we have infinity over infinity. That is one of the two standard forms. That's good. We can apply L'Hopital rule. So what do we get? We get 1 over 4 e to the power of 4x. And as x goes to infinity, this expression grows exponentially, so we get 1 over a really large number. The limit is 0. All right, and let's check this with the graph. Sure enough, we have as x goes to infinity, our graph is approaching the x-axis. Okay, so once again, we can check with the graph. All right, so what is the main trick here? Whenever we have the form 0 times infinity or infinity times 0, the order doesn't really matter. Okay, we're going to convert it to either 0 over 0, so that would be the first example here, and then or infinity over infinity. You saw that in the second example. Okay, and sometimes you will encounter problems where you can do either, and it doesn't really matter which form you would like to convert it to. Whichever one is more convenient, maybe easier for you to compute the derivatives. All right, so that is one of the non-standard indeterminate forms where we need to convert it into one of the two standards standard forms and then apply L'Hopital rule. Let's take a look at our last set of examples. Here we will take a look at the form 1 raised to infinity and infinity raised to 0. And for these examples, we will need to use a very specific trick. Now, in general, this type of problem seems to be a little bit challenging for students, so I encourage you to pay very careful attention to the solutions, carefully go through all the steps, and make sure that everything is clear. So let's take a look at the first problem. We would like to compute the limit as x goes to infinity of the expression 1 plus 1 over x raised to the power of x. So if we plug in infinity for x, that is a really, really large number, what does that look like? Well, 1 over x, that goes to 0. So we're going to get something like 1 to infinity. Okay, let's take a look at the solution. What is the trick here? The trick that we need to remember is we need to take the limit of the natural log of this expression. So if this is your f of x, okay, 1 plus 1 over x raised to the power of x, that is your function, then the trick is to take the natural log of that function and then take the limit of that. And you will see that halfway through the solution, we will also apply the L'Hopital rule. Okay, so here's the step. I'm going to take limit as x goes to infinity of the natural log of 1 plus 1 over x raised to the x power. And we do this because now we can take this x and bring it up front as a coefficient. And that is one of the rules that we know from the study of pre-calculus. Okay, so now we have the limit as x goes to infinity of the expression x times natural log of 1 plus 1 over x. And this is one of the forms that we just discussed. This is infinity times 0. Why is that? Well, as x grows, okay, we get infinity over here, and then natural log of 1, that's just 0, right? So that's where this form comes from. We know how to deal with this form. It is not one of the two standard forms, but that means what do? We need to convert it into one of the two standard forms. So the easiest thing to do is to rewrite x as 1 over x, and that's what I do over here. Okay, so now I have the limit as x goes to infinity of the expression natural log of 1 plus 1 over x over 1 over x. And that form is infinity over infinity. Okay, and now we can apply the L'Hopital rule. So we need to compute the derivative on top and the derivative on the bottom. Here is the computation. Notice that we have to remember all the rules here. It's 1 over 1 plus 1 over x times the derivative of the inside, which is negative 1 over x squared. Okay, and then the derivative of 1 over x is negative 1 over x squared. So these two cancel out. So we're computing the limit as x goes to infinity of this expression right here, and that's fairly simple. That's just 1. Okay, so that is our answer for now. This is not our final answer. And this is very, very important because it's a common mistake to just stop right here and say that's the answer. Now, let me remind you that we took the natural log of our function. Okay, that means we need to undo that operation. So 1 is not the final answer. The final answer would be e raised to this number, e raised to the first power, which is just e. Okay, why is that? Because if we took the natural log of our function at the start, to undo that, we need to take e to that power, right? So exponentiation is the inverse operation of taking natural log. All right, so this is very, very important to remember as you work through these types of problems, because your final answer will not be this intermediate answer, right? This was the intermediate step. The final answer is e raised to that power. All right, so that is our first example. Okay, now let's take a look at the second example that will have the same sort of steps. So what do we have here? We have limit as x goes to infinity of the expression e to the power 4x plus 9x raised to the power 1 over 5x. Okay, so what do we have here? We have an expression inside here that grows as x grows, right? So this is infinity. Okay, and then 1 over 5x. As x goes to infinity, this expression goes to 0, so we have this form of infinity raised to 0. All right, what is the trick? The trick is the same. We need to take the natural log of our function and compute that limit. So let's go through the step. Okay, so limit as x goes to infinity of natural log of e to the power of 4x plus 9x, all of that raised to the power 1 over 5x. Okay, so here's the step where I bring this down, okay, as the coefficient. And now I have the form infinity over infinity, right? Because I have natural log in the numerator. As x goes to infinity, so does this. So this goes to infinity. And 5x in the denominator, that also goes to infinity. Okay, so now we can apply the L'Hopital rule. All right, so what is the derivative of natural log of e to the power of 4x plus 9x? So it's 1 over the argument of our function times the derivative of that. So that would be times 4 e to the 4x plus 9. And then on the bottom, we just get 5. The derivative of 5x is 5. Okay, so we can clean it up over here. So I combined them to write it out in a slightly nicer form. And what do we do now? Now we'll look at the behavior of this function as x goes to infinity. We get infinity over infinity again. So we can apply L'Hopital rule for the second time. We get 16 e to the power of 4x on top. On the bottom, we get 5 times 4 e to the 4x plus 9. That is still infinity over infinity. So here we need to apply L'Hopital rule again. Okay, so we get 64 e to the 4x on top. On the bottom, we get 5 times 16 e to the 4x. And now these expressions cancel out. E to the 4x is a common factor. It's gone. So we have the limit of this constant term, 64 over 5 times 16, and that reduces to 4/5. Okay, let me remind you that this is not the final answer. This is an intermediate answer. The final answer is e raised to this power right here. Okay, so notice that this solution is somewhat tedious. Okay, there's a bunch of steps that we needed to do. We needed to take the natural log of the expression and then rewrite it as a quotient, right, using the rules of logarithms. Okay, check that we get one of the indeterminate forms. We did get it over here, and apply the rule carefully. Okay, so notice that computation can be a little bit tedious, right? There's a lot of stuff going on here, so we have to be especially careful when solving these type of problems. We apply L'Hopital rule here 3 times. Okay, and at the end, the final answer is e to whatever you get over here. Okay, and that is to undo this first step where we took the natural log of our function. Now, both of these results can be checked with a graph. I didn't do it for this particular slide only because the solutions are fairly involved and my pictures didn't fit well. Okay, but you can use Desmos to check your answer. So what you would do, you would plug in y equals to this function right here, e to the power 4x plus 9x raised to the power 1 over 5x, and then also plug in y is equal to e to the power 4 over 5. See what happens. Okay, you should have the graph of this function approaching this horizontal line as x goes to infinity. All right, so this is our last set of examples for this lecture. Let me do a very quick summary of what we've discussed in today's lecture. First, the L'Hopital rule can only be applied to limits with the two standard indeterminate forms, 0 over 0 or infinity over infinity. And here is an example where this rule is not applicable. Notice that if I plug in 1 for x into this function, 2x minus 1 over x squared plus 3, we do not get 0 over 0 or infinity over infinity. So in this case, we cannot apply this rule. And there are many other problems where we can't do it. So it is very important to check that condition. Whenever we evaluate the limit at the given value, where x is approaching, it must be either 0 over 0 or infinity over infinity. When applying the rule, do not use the quotient rule. That is also one of the common mistakes that can happen. Okay, just take the derivative on the top and divide by the derivative on the bottom. Next, whenever we have the form 0 times infinity, or in a different order, this needs to be converted to either 0 over 0 or infinity over infinity by applying some algebraic tricks. And then the form 1 to infinity, 0 to 0, or infinity to 0 that require computing the limit of the natural log of f of x, where f of x is the original function, right? Okay, so we have to remember to take the natural log, compute that limit, and let's say you get some value k, then the final answer is e raised to that value k. All right, and then it is not a bad idea to check your answer with a graph, especially with Desmos, which is very easy to work with. All right, we'll go ahead and stop right here. Thank you all for watching, and I will talk to you next time.